Okay, so we're going to be looking at the test statistics. So basically, we're going to be able to run some numbers now. We're going to check. Remember how last week I had you guys work on the null hypotheses and then the alternate hypotheses. And I also had you guys talk about type 1 errors, type 2 errors. Now, test statistic, I mentioned it last week. Test statistic is basically a value that we check if things work, and we have a formula here. X crossbar minus mu, which is the average of the study minus the average of the population, divided by, now at the bottom I have sigma. Sometimes I use the sigma for standard deviation of the population. Sometimes I use the letter S for the standard deviation of a study, of a sample. So remember, sometimes I could use S. Let me write my S there instead of the sigma, and then divided by the square root of n. N is how many, like the number of people that participated in my study. Okay, now there, I left you guys some space for the p-value, right? For you guys to be able to write it. Now that the p-value is basically defined as the probability under the assumption of no effect or no difference of the null hypothesis of obtaining a result equal to or more extreme than what was actually observed. Okay, so people will be like, what in the world did you just say, Mr. Leonzo? Well, the P stands for probability, right? So p-value stands for probability and measures how likely my results, whatever I just saw, happened just by coincidence. Okay? When we do a study, there's chance that we might make a mistake. So there's going to be the room for error. So we're going to use the p-value, and then I'm going to talk about later which p-values are good, which p-values are bad. But for right now, p-value is basically the probability that the results, anything observed between the groups, the null hypotheses, the alternate hypotheses, it was just by coincidence. Now we're going to use the one-tailed hypothesis of probability, the p-value. You guys see my two figures there. Here in this one, I have the null hypotheses. Let me the null average. Let me just call it that. This is when, and then I have the new average of my sample. If the sample that I have, what I'm trying to, is less than the null hypothesis, I'm gonna use the left-tailed test. So you guys see how my p-value is on the left-tailed of my normal distribution. Now, when my mu that I'm checking is bigger than the null average, then my p-value, notice, is on the right side of my distribution. So we call it the upper tail test. So when we have inequalities, it's the lower tailed or the upper tail test. You guys can see which one it is. Now, we can also have the two-tailed test. My p could be in two tails. Now, this one, let's say my average of the null hypotheses happens to be a negative number. Let's say in this case a -3, just to choose a number. Now here I'm checking that my probability, my average is not a negative number. So that's gonna give me these two tails. But then what if the null average was a positive value? Let's use +3. Now what I'm checking is that the average is actually not 3. It still gives me, as you guys can see, still gives me a two-tailed test. Okay. Now let's do as an example instead. That's gonna make more sense. Let's say a health journal conducted a study to see if packaging a healthy food product like junk food will influence children's desire to consume the product. Basically, if junk food looks nice, the packaging looks nice, would people buy it? Okay, so we have the study, what they're looking into. A fictitious brand of healthy food product, which they have sliced apples, was packaged to appeal to children. Now, the researchers showed that packaging to a sample of 327 school children. Let me let me see that 327, that's my N. Let me underline it because I'm going to use that. So they interviewed 327 school children and asked each of them whether he or she was willing to eat the product. Willingness to eat was measured on a 5-point scale, with 1 not willing at all and 5 very willing. The data are summarized as X crossbar, 3.27. The standard deviation of our sample is 2.53, right? And then suppose that researchers knew that the mean willingness to eat an actual brand of sliced apples, which is not packaged for children, that let's say the average is 3. Now state the null and alternate hypothesis. So we have the null hypothesis. We talked about this last week. The null hypothesis here, it is the average is 3. That's what they're telling me. Now, my alternate, in this case, on the notes, I didn't say which alternate I want to check. I didn't tell you guys whether it's a 1-tail p-value or 2-tail p-value. On the homework, I will. So let's just say that I want to check if my packaging, what I'm looking at here, is greater than 3. So I'm just going to say, I want to see if it is greater than 3. Okay, so that's basically my alternate hypothesis. Is my average greater than 3? Okay, so I want to use the 1-tail probability here. Let me find the test statistic. Remember the formula that I gave you guys on the top of the page? So I know the average of the sample is 3.27. And I know the average, the mu so far has been 3. I also know my standard deviation, in this case I use S because it's the standard deviation of a sample, is 2.53. And I know the N, the people that I asked, is 327. Based on the formula that is on the top, the way I'm going to find my C's value, my test statistic, I'm going to go X crossbar minus mu. So I'm going to go 3.27 minus 3. All of this divided by 2.53 divided by the square root of 327. Some of you might be like, oh my God, how am I going to type this? Okay. Let me help you guys out. Let me put the top, everything on top in parentheses. Let me put everything at the bottom in parentheses. And then on Canvas, you do have a calculator. This right here, I'm going to type it in on your calculator. Let me show you guys how it looks like. So let me share this calculator. Now this right here, radians, degrees, it doesn't matter. All right, we're not dealing with degrees here, so it's fine. I remember the top of my fraction, let me open parentheses. That's why I put it in parentheses. So do use your parentheses. I know it was 3.27 minus 3. And let me close parentheses. Right, that's what we had on the top of the fraction. Not a big deal. Divided by. Remember, it was across a big fraction. I'm going to open parentheses. So at the bottom, I had 2.53 divided by the square root. You guys see square root here? Square root of 327. Now let me close parentheses for the square root, and let me close parentheses for the bottom of the fraction. Again, One of them is because I'm closing the parentheses for the square root, and the other one I'm closing the parentheses for the bottom. See how I have everything that I had on top divided by everything that I had at the bottom. See? Now let me just press equal, and there's my number. There's my C value. There's my test statistic. Nice. Okay, now let me come back. I know in the instructions it said rounded to 2 decimal places. So this one, we know how to round. So this one I'm going to call it 1.93. See how simple that was? So let me come back here. My C value was 1.93. My test statistic, my C scored is 1.93 because I rounded to 2 decimal places. Now let me find the p-value. Okay. What's the probability that this happened actually by coincidence? Okay. Using that table, the C score that we have been using so far, I'm going to look at 1.93. You remember how you guys know how to read that? It gives me a probability. I'm going to say 1.93. It gives me a probability of 0.4732. Remember, you guys have the table. So it gave me 0.4732. Now, what does that mean? Okay, let me come back here. Obviously, we do have a one-tail figure. That probability is this space right here, 0.4732. But I'm not interested in that. I'm interested in this place. How much is that? Notice how it is half of our distribution. So I'm just going to go 0.5, because remember how all of this is 0.5 minus 0.4732. That's it. That's all I'm going to do. So let me go 0.5. So 0.5 minus 0.4732. Use your calculator if necessary. And well, this one gives me 0.0268. But it says rounded to 3 decimal places. Oh, okay. 3 decimal places. So my answer will be 0.027. That's my p-value. Not that bad. Okay, what does the p-value do? It tells us whether we're going to accept or reject the null hypotheses. We're going to talk about that in the next lecture. So for right now, I just found my p-value. That's it. Now, let's do it again. A health journal conducted a study to see if packaging a healthy food product like junk food will influence children's desire to consume the product. Okay, so we're looking at another study, whether we sell junk food looking nice, whether people will actually want to buy it. Fictitious brand of a healthy food product, we have sliced apples, was packaged to appeal to children. The researchers showed the packaging to a sample of 394 school children. Okay, so my sample, my N, the number of my sample is 394. Let me write that somewhere over here. N equals 394. Okay, these children were asked whether he or she was willing to eat the product. Willingness to eat was measured on a 5-point scale, from 1 to 5. And the data was summarized as my average of the study to be 3.66, my standard deviation of the study to be 1.89. Suppose that researchers knew that the mean willingness to eat an actual brand of sliced apples, which is not packaged for children, is 3. The average is 3. Now, state the null and alternate hypotheses. And again, like here, let me just told you that the one thing we're going to be checking that it has changed, that the average was 3. Now I'm going to say, what if it has changed? So I'm looking at my mu, not 3. That's what I'm going to check. So I don't want to check for greater than now. I want to check what if it's not 3. Okay, so let's see. My null hypothesis, I being told that the average is 3. Right, so regular bags of sliced apples is 3. My alternate hypothesis, I'm gonna say that the average is not 3. I wanna see that the packaging of these apples actually changes, whether the number goes up or the number goes down, right? It is not 3. Now let's find the C statistic, the C score, from our test statistic. I know that my X bar, I have to go X cross bar minus mu, divide this by the standard deviation. Sometimes I use sigma, sometimes I use S, depending on what I'm looking at. So my standard deviation divided by the square root of n. So in this case, I'm gonna go 3.66. Let me write this in blue instead. 3.66 minus 3 over 1.89 divided by, I don't have to write it as a fraction. I can just write divided by the square root of 394. That way we're going to type all of this. Remembered, previous question, I use parentheses. I'm going to put everything on top inside on parentheses divided by everything that I have at the bottom inside parentheses. Let me open my calculator here. Let me clear this out. So open parentheses. 3.66 minus 3, close parentheses. So the top was not that bad, right? Easy to type. Divided by, open parentheses for the bottom. 1.89 divided by the square root of 394. Close the parentheses for the square root and close the parentheses for the bottom. And I'm going to type this in, and it says, I know my instructions, it says round it to 2 decimal places as needed. 6.93. Not bad. Okay, so let me come back here. Was my test statistic, was my C value? It was 6.93. Now I gotta find my P value. But looking at my table, I notice it doesn't go to 6.93. It actually stops at 3.99. Right? 3.99, that's the highest. 6.93, it's not even on my table. Now, why is that? Because the table, the C-score value that it was giving us, notice how 3.99 pretty much approaches 0.5. Okay. So, but let me show you guys something here. So when my C-score was 3.99, my C-score is 3.99. This space is 0.5. Right? The shaded area is 0.5. So guess what? This left side, this space right here is 0. Oh, no, not that. Not that. That's not the 0.5. This is 0.5. So it means this shaded area here is 0. Right? Because remember how this whole half was 0.5 and this empty space is already 0.5? So if my C value gets bigger, well, my 0.5, my probability cannot get bigger because I already have all of it. This little shaded area, it's so small that it is insignificant. After 3.99, that shaded area is so small that is basically 0. Not exactly 0, but so small. Some of you guys might be wondering, what's a number that is very small? Think of $20. But go ask a billionaire How much is $20 to you? And they're going to say it's a number that's very, very small, very insignificant to them. So let me come back here. If 3.99 is 0.5, right? This area is 0.5. That means the p-value is 0. Well, what will 6.93 be? Well, anything after 3.99 is 0. The shaded area is 0. So guess what? For 6.93, it's still 0. It's here it says rounded to 3 decimal places. So fine, I'm gonna use 3 decimal places. 0.000. When my C-score is too big, I'm just gonna say 0.00. Now, some of you might be wondering, Mr. Leon, so this p-value thing, it was a two-tail. Okay, so I had this other space right here, right? This is 0. This is 0. Add them up. It's still 0.000. Let me come back a little bit on my probabilities. When I had an inequality, I had a one-tail probability, a one-tail p-value. So the value that I got, that was it. When I had the not equal to sign, I have two tails. But in my cases, my tails were zeros, were very significant. So when I added the two tails, so when you have the not equal to, you have to multiply by 2. My p-value still came to 0. Let me zoom out. That way you guys can see what we did today.